can you hear me?
Yes, I can hear you. Thank you.
Great, and I can hear you. So our next talk will be given by Antonia Wachter-Zeh from the Technical University of Munich. I'm very glad she could join us via Zoom. So I'll let you take it away.
Thanks a lot for a nice introduction. So thanks for letting me give this talk online, and it's great that you come to listen to it anyways. Okay, so I'm going to talk about interleaved rank metric codes for cryptography. Let's switch. Okay, let's start with the basic encryption model that we are considering here. So we have Bob, who wants to encrypt a secret message and or who wants to transmit a message to Alice, but doesn't want Eve to read the message, and therefore Bob encrypts the message to a ciphertext. Now, in classical cryptography, we basically have two possibilities of doing this encryption, either by symmetric encryption, which means that both parties, so Bob and Alice, somehow have the same secret key and use it for encryption and decryption. Of course, the secret key has to be shared beforehand via some secure channel. And in order to enable such a secure channel to exchange this key, what's usually done is to use public key cryptography, asymmetric encryption, where Alice creates a key pair, her public key and her private key. She keeps the private key to herself and doesn't share it, and the public key she can share to anyone, so she can, for example, publish it on her website. And now Bob can use her public key to encrypt messages to her, but only Alice can decrypt them by using the secret key. Okay, so anybody with a public key can encrypt, but only Alice can decrypt. And that's basically the setting that we'll consider here. The motivation why we look at code-based public key cryptosystems basically comes from quantum computers. I'm not talking about this here now, but as soon as capable quantum computers will exist, classical public key systems like RSA or elliptic curve cryptography will be fully broken. So we definitely need alternatives for this. And there are like standardization efforts, for example, by the NIST for post-quantum secure encryption and signature schemes. Okay, but now let's go to coding theory, which will in the end be used for cryptography. So we'll start with something which is called interleaved Hamming metric code. That's actually an old concept, and we can just easily show it by Reed-Solomon codes. So assume you have L Reed-Solomon code words, and you just write it into the rows of a matrix. And that's it basically already. So if your Reed-Solomon code is defined over FQ, you can also see this matrix with L rows as a vector over the extension field FQL. And now they're like, you can make some distinctions. So first of all, like all rows are from the same Reed-Solomon code. Then you can also see the extension field representation as a shortened RS code over the extension field, or if they come from different Reed-Solomon codes, which might have different dimensions, you're more flexible, but it's not a Reed-Solomon code over the extension field. But that's not so important here. Where do these interleaved codes actually make sense? They make sense if we have a certain special error model, which is called burst errors, meaning that if you look at the matrix representation, they basically corrupt whole columns of the matrix. And of course, in the extension field, it's like elements, symbols of this vector. And then if you really go into syndrome-based decoding of Reed-Solomon codes, you can set up a key equation for each of these rows and then decode jointly. So if you're not familiar so much with syndrome-based decoding of Reed-Solomon codes, it doesn't matter. So what's the important thing here to see is that all the Reed-Solomon code words, all L code words are affected by errors at the same positions. And one step in Reed-Solomon decoding is in syndrome-based decoding is to find a polynomial, that's this lambda, the error locator polynomial, that basically has these error positions as roots. Now, if we want to find this unknown error locator polynomial, we usually just have one corrupted code word, or just a single code word, so we can solve this linear system of equations. Now we have L of these linear systems of equations, meaning we have more equations for the same number of unknowns, which in turn actually means that we can increase the number of unknowns and therefore we can tolerate more errors. That's like the high level idea. Yeah, so that's also shown here now. Now this is the syndrome matrix for one of the rows. For the L rows, these are the syndrome matrices. Now the lambda is the unknown, and now we can solve for this polynomial and hopefully find the error locations. Yeah, of course, you can only gain if the equations are linearly independent, meaning if the second syndrome matrix is exactly the same as the first, of course, you don't gain anything. Now, if they are linearly independent, you can just, from the number of unknowns and equations, you can calculate a decoding radius, which is then this one. So it's L divided by L plus 1 times D minus 1. And you can see already that if you put L equals 1, which is just the standard Reed-Solomon decoding case, it's exactly D minus 1/2. So the usual unique decoding radius. Now, of course, that only works if the rank of this matrix is full. And there's a certain probability that it's not, which we call the failure probability. It's approximately 1 over Q minus 1. So for large Q, that's rather small. Okay, meaning that with high probability, these interleaved Reed-Solomon codes can be decoded up to here. Now there's also another result on decoding codes of high interleaving order. This holds now for any linear code in the Hamming metric, so not only Reed-Solomon codes, but any linear code. So if you have a very large interleaving order, that means L is at least the number of errors, then there's an approach that actually guarantees correct decoding for any error matrix of rank T. So if this error matrix has rank T, then any linear interleaved code can be decoded, and it's guaranteed to get a unique result back. Meaning that if the interleaving order is really large, it doesn't even have to be a Reed-Solomon code. And we will see why this is important for cryptography later. Yeah, let's speak about this later. So that also means that decoding a random linear interleaved code with when the interleaving order is large is an easy problem. Okay, so we will see later how cryptography can be based on decoding a random code. And in that case, so if it's an interleaved code of large interleaving order, then it's easy to decode. Okay, we can look at this now. So this is the classical McLeese cryptosystem. So that's really like the easiest way to formulate it. That's not how it's done, for example, in the NIST submission classic McLeese. But just for those who are maybe not familiar, it's maybe the easiest to understand the principle. So this is a public key cryptosystem. So as mentioned before, Alice creates a private key and a public key. So for the private key, she chooses 3 matrices, where G is the generator matrix of a T error correcting code. So it can be, so yeah, in classic McLeese, it's a Gopper code. And she also chooses S and P, where S is just a random full rank matrix and P is a random full rank permutation matrix. Then she calculates the product of these 3 matrices, which is called GPUP. Now GPUP should look random, so GPUP shouldn't tell anything about G. I mean, the type of the code, it's a Gopper code, it's public, but the locators, for example, are not. So it should be hard to get from GPUP to G. Now for the encryption, Bob basically encodes the message with GPUP and also adds an error, a random error of weight T. Now if Eve would want to read the message M, she would have to do decoding in the code defined by GPUP. And now since GPUP should look random, that's supposed to be a hard problem. And only Alice, by using these other 2 matrices, can reduce this decoding problem to decode in the code generated by G, which will be easy. Okay, now of course we can also just modify it to use interleaved codes. Basically, we split our message into L parts and then create L ciphertexts and choose the errors in a suitable way, basically as bursts, and such that they are linearly independent, and do the whole thing as here in classic McLeese. Now we see already if we do this, and we have these interleaved, let's say, Gopper codes, if the interleaving order is very large, so as said here, larger than t, then also Eve can just do decoding, because Eve can then also decode in this GPUB if the interleaving order is large. Okay, so that's of course what has to be taken care of, that the interleaving order is not too large. Okay, so the decoding radius for these interleaved copper codes can be shown to be increased to this radius. So that's the interleaved decoding capability of interleaved white copper codes, instead of this is the unique decoding radius. And then you can, in the end, if you recalculate it, then you can see that since you now can tolerate more errors, you can in the end decrease the key size for the cryptographic key size, which is an important performance parameter. Okay, so that's how you could use interleaved copper codes for cryptography. But now I said in my talk title that I want to talk about rank metric codes as well. So let's shortly introduce them here. So the high-level idea is basically that we consider matrices of size m by n, and of course there's a one-to-one mapping of the matrices of size m by n over fq to vectors of length n over the extension field fqm. And now the rank distance between two matrices is just the rank of their difference. So that's defined as DRAB. And now if we look at a rank metric code, then it's basically, we can say that it's m by n matrices over fq, or we can see the code words as vectors of length n over fqm. And it's a, and if we use this notation, it's a linear rank metric code. Now there's also a singleton-like bound, and codes, there exist codes that attain this bound, which can somehow be seen as the analog of Reed-Solomon codes. So maximum rank distance codes, for example, the Gabby-Dooling codes. Okay, now if we want to use, for example, Gabby-Dooling codes or other rank metric codes in cryptography, we have to look at hard problems. So this is now the rank syndrome decoding problem. As a remark, if we look at this in the Hamming metric, to the syndrome decoding problem, that's proven to be an NP-hard problem. Now, how is the problem defined in rank metric? So here the problem is that given the parity check matrix of size n minus k by n and a syndrome, we have to find an error vector such that h times e is syndrome and the rank of the error is upper bounded by t. Okay, so that's the classical syndrome decoding problem just in the rank metric. Now there's another decoding problem. If we look at FQ linear codes, this is basically the min rank problem. So it looks a bit different, but in the end, it's the decoding problem for codes that are only linear over FQ and not over FQM. So assume we have these K generator matrices over the field FQ of size m by n and some received matrix. Now we want to find these coefficients m0 up to mk minus 1, such that the rank of this thing is at most t. So that's basically, you can see it as an error. So this is the received word. This is a code word because it's generated as a sum over these generator matrices, and you want to find the error that has the rank of at most t. Now, for the min rank problem, it can be proven that it's NP-hard, basically by transforming an instance of the Hamming syndrome decoding problem into an instance of the min rank problem. That works by putting the Hamming metric code and received words on a diagonal. But for the rank syndrome decoding problem, it's just the hardness is only proven under a randomized reduction. So this is maybe something that's a bit of disadvantage over the rank metric compared to the classical syndrome decoding problem. Okay, but now we can also, we see that we have these problems that are somehow hard. So now we can think about, can we build code-based cryptography based on it? Can we maybe even do, as we did before, something based on interleaved codes? Okay, so let's have a look at interleaved rank metric codes. Now there are two possibilities. So before, when we were looking at the Hamming metric, only this made sense, because otherwise if you have something like that, that's a bit weird. But now here, if we look at matrices, we can just put the matrices, arrange them like that, or like that. Okay, so now we are speaking about vertical interleaving and horizontal interleaving. depending on how we arrange the code words. Now, of course, we also have to speak about the error model. So recall that in the Hamming metric, we had these L code words below each other, and they all basically had the same error positions. Now here we are in the rank metric, so error positions do not really exist because we talk about the rank of error matrices. So the equivalent burst error model here is, first of all, that the rank of the overall matrix is limited. So in both cases, the rank of the matrix E is at most T. So if you look at the corresponding matrix built from these L matrices, either this one or this one, the rank is at most T. In the vertical interleaving case, all these E basically share a row space. And in the horizontal interleaving case, they share a column space of dimension at most T in both cases. Okay, so you can basically have these two models of interleaving. Now, I mentioned shortly Gaby-Dulin codes, which are basically like the analog of Reed-Solomon codes. Now, this is a vertical definition of an interleaved Gaby-Dulin code, where you put, just as in the Hamming metric case, the code words as rows into an L by N matrix. That works pretty much as Reed-Solomon codes. And if you go through all the analysis, it also looks like very similar. So you can get the same maximum decoding radius as for interleaved Reed-Solomon codes. And it works also with high probability. You can get the same radius also for horizontal interleaving. Okay. Now, if we look at the high interleaving order, which is L is larger than T, then if we do the vertical interleaving, we can get a similar algorithm and statement in the case where if we consider the error matrix here in this of this size as L by N error matrix over FQM. And if this has rank T, then we can also always do unique decoding for any linear interleaved rank metric code. So there, if we use like the McLeese principle that basically hides the structure of the code, again, we shouldn't use a large interleaving order. So that means decoding a random linear vertically interleaved rank metric code is an easy problem. But what about horizontal interleaving? And now the thing is, I mean, straightforward, probably everybody would say like, okay, we can do the same thing also, but it just doesn't work. So if you try to adapt the algorithm, there are always things where it doesn't work out. And in fact, the horizontal interleaving problem is equivalent to something called the rank support learning problem. So that's shown here. I don't want to read it now, but it's basically the same as decoding horizontal interleaved codes. And the thing is that this rank support learning problem has been used already in cryptography for a few schemes. And there exist multiple papers that actually analyze this exponential complexity, which somehow hints that probably for the case of decoding horizontally interleaved rank metric codes, there's no such nice algorithm that works for any linear code as here for the vertical case. Or maybe just you need a different perspective to make it work, and then you can break the rank support learning problem. Okay, so now if we have this, we can have a look how it behaves if we apply this to rank metric codes. Now this is the so-called GPT cryptosystem after its inventors, Gaby-Dulin, Paramonov, and Tretyakov. It's basically the McLeese system in the rank metric, also here in its simplest version. So now the difference to classic McLeese or to the McLeese system as I presented it before is basically now that this G matrix is the general matrix of a Gaby-Dulin code. And instead of having a permutation matrix here, we need a random full rank matrix over the base field. That's important that it's over the base field. And then again, GPUB is the product of these matrices and made public by Alice. And now the encryption is again encrypting in this public code and adding a random error. Now for Eve to recover M would have to do decoding in this randomly looking code GPUB. Now, if you do this with Gabby-Doolin codes, then there's a distinguisher, which means that you can actually say whether GPUB was chosen randomly or comes from a Gabby-Doolin code. And then there's actually also an attack based on this distinguisher. So the idea of the distinguisher basically means that if you use this, what's called the Q-sum of Gabby-Doolin codes. So if you take a matrix M and then append the matrix M power Q, meaning each element taken by the power of Q, then each element taken by the power of Q squared, and so on, up to Q power F. And if you look at this matrix, so that's called the Q-sum, if you have the generator matrix of a Gabby-Doolin code here, then this matrix has rank only the minimum of n and k plus f. That's basically because of the structure of the Gabby-Doolin code. Now, if you really have just a random generator matrix, then with high probability it has this rank. So just from the rank of this GPUB, so you're applying the Q-sum on our GPUB here, and then analyzing its rank, you can see whether it comes from a Gabby-Doolin code or if it's a random code. And basically, based on this distinguisher, you can also build an efficient key attack, which breaks the GPT system and its generalizations. So it's not a good idea to use plain Gabby-Doolin codes here. Now, what you can do, what was done by Pierre Lodot and so far hasn't been broken, is to repair it by a so-called subspace scrambler, which basically means that you have a matrix T. So that's not now it's called T instead of P. And now T has basically, or T inverse has entries from a lambda dimensional subspace. And by this, without going into detail, this whole Q-sum attack doesn't work anymore. Okay, but we wanted to talk about interleaving. So now we can use this subspace scrambler-based GPT system and look at interleaving of this system. So one thing is to do vertical interleaving. Basically, you use Lodot's system, and now you just, again, you split your message into L parts and then encrypt it into L ciphertexts and add an error EI, where now the errors have a joint row space, and then you're able to have that many errors. Now, if you look at the parameters that you see a slight improvement then compared to the classic Lodot system. Again, so a bit at the drawback that you get a decryption failure right now, which comes from the interleaved decoding case. Okay, so that's also why doesn't it improve that much? The thing is that we cannot have high interleaving orders here, because otherwise Eve could just use the general linear high interleaving order decoder. But if you use horizontal interleaving of Lodot system, basically the same way. Now here it's written in the Niederreiter form, so with parity check instead of generator matrices. But in the end, this doesn't make a difference. Again, we choose the errors as a horizontal rank metric birds, meaning they share the same column space. And now you get multiple ciphertexts or multiple syndromes, however you consider it. And then you can really reduce the public key size by quite a bit. So that's the interesting thing. Okay, so that already brings me to my conclusion. So interleaving is actually a nice tool for code-based cryptography to play with the parameters to tune them. There's still a lot of interesting open questions. So first of all, you can do interleaving in many other metrics, like, for example, the sum rank metric. There are some results on the sum rank metric already, but there's still a lot of things to be done. That's actually, I think, the most interesting thing, to look at the horizontal interleaving of rank metric codes. It's a bit strange on the first glance that everything works out nicely for vertical interleaving, that you can do decoding of any linear vertically interleaved rank metric code for high interleaving order, but you cannot for horizontal. That is a bit strange, so maybe it's really a hard problem that would be interesting to prove, or vice versa, maybe taking the tools from interleaved coding theory, it's possible to consider the rank support learning problem from a different perspective and maybe find a more efficient algorithm to solve it. Then there are also other systems where you don't hide the structure of a code, like, for example, RQC or HQC. So it would be worth a try to understand what if we do interleaving there, because then we don't have to hide the code structure. Then, of course, that's like the GPT system that's broken for classical Gaby-Dooling codes. Can we do it differently without the subspace scrambler? Because this basically hurts the parameters a bit. And then these are three rank metric based systems based on different principles which are broken. So it would be interesting to repair these schemes. They are basically connected by one approach. Then one thing is also rank metric, maybe interleaved signature schemes. So there are a few signature schemes submitted now to the next NIST competition on signature schemes. So maybe it's worth looking how to use interleaved rank metric codes. And yeah, so proving the hardness of the rank syndrome decoding problem without probabilistic reduction is also an important problem. Okay, that brings me to the end of my talk, and I'm looking forward to your questions. But before that, I still want to make an advertisement to our workshop, to our Munich workshop on coding and cryptography, which will happen from April 8 to 10 this year, with a special focus on post-quantum cryptography and privacy for machine learning. So we would be happy to see many of you there. You can find a list of speakers and everything already online. Thanks a lot.
Thank you, Antonia. All right. Questions? Let me get you the mic.
Thank you very much for the nice talk. I don't work on cryptography, but so this might be naive, but could you say a little more about the motivation for that burst error model? That's my first question. The second was, you mentioned the rank metric when you represent them as matrices, but when you do the vector representation over the extension field, what is that distance? Like from the rank distance becomes what vector distance?
Yeah, okay, let's start with the first one. So the burst error model, there are some, so one motivation in the classical Hamming metric comes from concatenated codes, where you basically, if like one of your inner code words is completely destroyed, you get the structure of burst errors. But here in cryptography, it doesn't matter, because like if we look at the McLeese system, Bob basically chooses the error. So of course we can choose the error as we wish. I mean, we can define a system where basically the encryption algorithm states or makes that all the errors have this burst structure. Okay, so because we can design the errors, it's not, we don't have a channel. We are really like we're doing the encryption, so it's like some artificial channel where we can design the errors. Okay, and now for the rank metric codes. So what was your question? What happens with the rank distance over the large field?
Yeah, so the rank distance is clear when you represent using the right representation with the FQ m by n, but when you represent it as the small vector a, what is that distance? The induced distance, if you like.
Yeah, I mean, it's defined in the matrix representation, right? I mean, if you look at two vectors, you cannot directly see it. You can look at the Hamming distance, but the rank distance can be 1, and the Hamming distance in the vector representation can be n. So like if the difference of these two matrices is, for example, an all-1 matrix, all entries are 1, the rank is clearly 1, right? But then if I map it on a vector, it's a vector that has a non-zero entry everywhere, so the Hamming weight would be n.
I was just curious if there's a different metric than the Hamming metric that captures the rank distance, but maybe not.
No, it's just defined over the base field. You cannot see it from the extension field representation.
Thank you.
Thank you.
Thanks. If I can also ask a quick question. On the last slide, you mentioned this, I believe it was sum rank metric you said. I don't think I've heard of that before. Can you quickly define it?
Yeah, so the sum rank metric, it's basically defined. You have a vector that consists of multiple blocks. And now the Hamming weight and the rank weight, and the sum rank weight is basically the rank of the first block plus the rank of the second block plus the rank of the third block and so on. So it's an intermediate thing between rank and Hamming metric. So if the block size is just 1, you get the Hamming metric. If you just have a single block, it's just a rank metric.
Gotcha. Thank you.
All right. I actually have one question regarding this RSL problem. You mentioned there's people have designed exponential complexity algorithms. Is it known if this is NP hard or the hardness more generally?
Yeah, I don't think that there's much known about the hardness. It's just people believe it's hard, and therefore they, well, there are like the best algorithms that can solve it have some exponential complexity, and therefore they built these crypto systems based on this problem.
Great, thank you very much. So let's thank the speaker again, and we will move on.
Thanks a lot, everyone.